Welcome to the presentation on chemical bonding. It says, I believe that there are, and then I don't even know how to say this number, protons in the universe and the same number of electrons. It's an estimate by Sir Arthur Eddington. And you also see the chemical compounds of ionic bonds in the nucleus. You know I don't speak Spanish. In English, please. So the learning goals for this presentation are that students understand the type of chemical bonds that form between atoms and understand the properties of the atom that lead to the formation of chemical bonds. So first, we need to look at what's called the octet rule. Atoms tend to be most stable when they have a filled valence shell or a filled orbital valence shell. So for most elements, or for all elements that are less than 36, that means that they follow what's called the octet rule. The reason being, if you have a complete s orbital and a complete p orbital, that together, when you add those up, comes up to a total of 8 valence electrons. If you were to look at the far right side of the periodic table, that would give you the noble gas column would be where you have 8 valence electrons. Now this is only for elements that are less than 36, because once we get bigger than 36 we have to account for the d and the f orbitals. And we're not going to do that at this point. So we're just going to say that the octet rule is where atoms want to be. Now there are a couple of exceptions to the octet rule, even when we're talking about less than 36. Greater than 36 is because of the d and f orbital. But there are exceptions less than 36, and that's with hydrogen and helium. Both of those are stable with only an s orbital. So if they're stable with only an s orbital, that means they only need 2 electrons. You can create what's called a Lewis dot diagram, and a Lewis dot diagram is a way of referencing the valence electron structure of a particular atom or series of atoms. What you do is you draw only the valence electrons. Now the valence electrons represent the electrons that are in the outermost orbital. So if I have a proton, or excuse me, a nucleus, and then around the nucleus I have the various orbitals. For lithium, lithium has 3 electrons. So there's 2 in the inner, or 1 energy orbital, and there's 1 in the outer energy level. So there is only 1 valence electron in lithium, which is drawn right here. You can figure out what the Lewis dot structure is by looking at the columns of the periodic table. Everything in group 1 has 1 valence electron. Group 2, group 3, group 13, group 14, and group 15. Now it keeps going on, group 16, 17, and 18. Now we do skip groups 3 through 12 because those represent the transition elements. Now the Hund's rule is how we figure out how we're going to fill these things. Now this is actually the incorrect representation for carbon, and we'll actually talk about that a little bit later. But this is not energetically correct for carbon. So it says a new element is discovered with the Lewis dot structure of this. What chemical family does it belong to? So if you look, I have 6 total valence electrons. If I have 6 valence electrons, that's going to put me in group 16 of the periodic table, which is on the far right. It's almost close to the noble gases and the halogens. So this is actually called the chalcogens, which is kind of an archaic name for it, or you can refer to it as the group 16. Either one of those would be a correct answer. Now I know it's going to belong there because of its valence electron structure. Now I would need to know more information about its atomic mass or how many energy levels it would be to identify its exact position on the periodic table. Okay, it says the octet rule is really more of a general guideline than a rule. You get the element, the molecule boron trichloride is more stable than boron tetrachloride. Using your knowledge of electron orbitals, speculate on why this is the case. So once again, we're speculating. Okay, we're not going to know the exact answer, but we know that boron initially has 3 valence electrons. Now realize that a chemical bond is formed whenever 2 atoms share electrons between them. Well, if I were to share an electron, I can share an electron and chlorine can share an electron, and that forms a bond. This one can share an electron and chlorine can share an electron, and that would make a bond. Same thing with this one. In order for a 4th bond to form, chlorine would have to contribute 2 electrons to the bonding pair, and that's not stable for either one of the elements. So boron tetrachloride does not tend to be formed because there's no electron for boron to contribute to the bond. The first type of bond we're going to examine is an ionic bond. Ionic bonds can be represented by the Lewis dot structure that you see below. What you see is that sodium initially has 1 valence electron because it's in group 1, and chlorine has 7 valence electrons because it's in group 17. So because of that, this is the initial setup. When the compound sodium chloride is formed, though, the electron is actually removed from the sodium and it goes to the chlorine. So now chlorine has 8 valence electrons where before it had 7, and sodium, depending on how you look at it, either has 0 valence electrons where it once had 1, or you can think of it as having 8 valence electrons. And people say, well, what's the difference between the two? Sodium initially is a proton. It has 2 electrons in its inner orbital. It has 8 electrons. 4, 5, 6, 7, 8. It's got 8 valence electrons, or excuse me, electrons in the next orbital, and then it has a single electron in the outermost, so it only has 1 valence electron. Now, when this 1 electron is removed, this orbital is no longer the valence shell. This is now the valence shell. So since this is the valence shell, there are 8 valence electrons. So in this case, both atoms satisfy the octet rule when an electron is removed from sodium and transferred to chlorine. Okay, whenever you have something that's a positive ion, or a positive that has more protons than it has electrons, it's called a cation. Now, cations tend to be formed in group 1, 2, 3 through 12, and group 13. They are more stable when they have less electrons than they do protons. Example of that is lithium. You see lithium right here. This is the initial atom for lithium. It has 2 inner electrons and then it has 1 outer electron. That's not stable because it doesn't satisfy the octet rule, and it doesn't satisfy the exceptions to the octet rule. I can remove an electron from lithium and then I satisfied the octet rule. And you say, well, there's not 8 electrons. Yes, but remember, this is an exception to the octet rule. The other option that I could have is I could actually bring in 7 different electrons. And if I bring in 7 different electrons, it would also be stable. But it is more energetically favorable for lithium to lose 1 electron than it is for it to gain 7. It's more likely to occur. So because of that, we can say that lithium tends to form +1 ions. If you have +1 ions, or if you have cations, you need to be able to form anions as well. Now, anions tend to be formed in group 15, 16, and 17, and they are more stable whenever you add electrons or when there are more electrons than there are protons. So once again, you see the example of fluorine that's here. With fluorine, actually these are both drawn wrong. These are both missing 2 electrons, and when you put the 2 electrons there, excuse me, there you go. This is fluorine. Fluorine has, if you look, 7 valence electrons, and that's not stable. Okay, the fluorine ion has 8 valence electrons, and it is more stable because it's completed its orbital shell. Ionic bonds. So what's formed between the 2 ions, a cation and an anion? I have a cation that's positive, and I have an anion that's negative, and those 2 things are attracted to one another by Coulomb's law. Remember, opposites attract. So because there's opposites attract, or because there's a positive and negative charge, this is a very, very strong attraction between the 2. This is a plus whole number charge. So these ionic bonds involve whole number charges. Okay. The reason why we're specifying that is later we'll talk about something called a partial positive or a partial negative charge. So for now, we need to look at it from this perspective. So you have a cation and you have an anion. Now, the ionic bond generally forms between metals and nonmetals. Okay, everything that's in group 13 to the left is considered to be a metal. Everything that's in group 15 to the right tends to be a nonmetal. Now, like we said before, this is an extremely strong bond, and therefore it requires a large amount of energy to break. Not only that, but ionic compounds tend to have very high melting points and very high vaporization points because the amount of energy needed to break or loose or remove something from this ionic bond. Now, it is a highly exothermic reaction, which means that it tends to produce heat whenever you have an ionic bond that's formed. What we have is called the lattice energy, and what happens is you have stacks of cations and anions together, and they tend to form no definite shape. And that's why you tend to see these things, they're brittle because they can easily move from one side to the other. They can just kind of shift. But what the lattice energy is, how much energy it takes to go from a solid crystal structure to a gas. And that's an extremely high amount of energy. So you tend to see these lattice energies tend to be very, very, very large. Now, one thing that you'll see is that the lattice energy actually increases as the charge increases, and that should make a lot of sense. If I have two ions, +1 and -1, they're going to have some sort of attraction between them. But if I were to take the two identical things and just replace it with +2 and -2, the attraction between them is going to be much greater because the charge between them is greater. So the greater the charge, the greater the energy required to remove them from each other. So we know that ionic compounds tend to be solids at room temperature. There are things like table salt, or potassium chloride, or copper sulfate. These things all tend to be solids at room temperature because of the ionization energy, because of the energy required to make them move. They tend to have high melting points and even higher boiling points, and they tend to be very, very brittle. It's not on order or out of order for the melting point of an ionic compound to be somewhere around 3,000 to 4,000 degrees. If you contrast that with something like water that boils at 100 degrees, that's a pretty significant difference. Now, we need to review naming ionic compounds. You're familiar with these. You should know them. You should have already memorized your polyatomic ions, and we're ready to go. But the cation is always named first, and then followed by the anion. And you need to make sure that whenever you're writing out the formula, that the charges balance out to 0. Okay. Next, so it says name the ionic compounds below and place them in order of decreasing lattice energy. So the first thing we need to look at is we're going to look at the lattice energy. Barium is a +2 charge. I know that because it's in group 2. Phosphate is a -3 charge. So the first thing that you should realize here is this is not the correct formula for this particular substance. It should be PO4 2. So now that we have fixed that, we can go ahead and say which one is going to be greater. So we've got a +2 and a -3. We look at the next one. Potassium is in group 1. Sulfate is a -2 charge. And then finally we have +1 and -1. So we can say that these things are actually in order of decreasing lattice energy. Barium phosphate is going to have the greatest lattice energy because it has the greatest charges that are pulling them together. Okay, potassium sulfate is going to have the next greatest lattice energy because it has a higher charge than sodium chloride. So these are actually in the correct order. Now, if I'm going to name these things, this right here is barium because it's the cation, and then I would have to name this would be phosphate. This is potassium because it's the cation, and then the second part is the sulfate molecule. And then finally you have sodium and chloride. The second type of bond we need to talk about is called a covalent bond. Where ionic bonds form when electrons are removed or added to an atom, covalent bonds form whenever the electrons are shared between each other. So whenever we talk about a covalent bond, we're not talking about taking something away from somebody. We're talking about two different atoms sharing the same set of electrons. A covalent bond has to occur between two nonmetals. So these tend to be things that are group 14 through group 18. Okay, so that tends to be where we find covalent bonds. Occasionally, or not occasionally, you also see hydrogen added to that. Hydrogen is allowed to form covalent bonds, but other than that, those are the substances that form covalent bonds. The molecules are different from ionic bonds because they have a definite shape. You're going to see a molecule that looks like this, as opposed to some sort of lattice structure where it's just where the molecules tended to stick. Okay, these covalent bond substances tend to be gases or liquids at room temperature. They have very low boiling points, especially when compared to ionic substances, and very low melting points as well. So here you see an indication of how the electrons are being shared between these two particular atoms. If you were to look at it on the valence structure, if you count these two electrons for the top atom, it has 8 valence electrons. If you were to count these for the bottom ones, it would also have 8 valence electrons. So even though there's not a total of 16 valence electrons, each atom thinks that it has satisfied the octet rule. Sharing equally. So electrons can be shared equally between two atoms. Whenever they're shared equally between each other, it's called a nonpolar bond. Now, how do you determine if it's shared equally? You look at what is called the change in electronegativity value. Now, we've already discussed the electronegativity. It's the affinity of a particular atom to have electrons or pull electrons towards them. So that creates what we call a nonpolar bond. and you can figure it out by the change in electronegativity. So these atoms that, or excuse me, these molecules that tend to form non-polar covalent bonds almost always are the same substance. Okay, those are the ones that are going to be perfectly non-polar. In other words, this chlorine atom is going to pull on these electrons just as much as this chlorine is going to pull on these electrons. So anytime you have what's called a diatomic, it's going to be a non-polar bond. Now that doesn't mean those are the only non-polar bonds. In fact, whenever you have something like this, a CH bond, that's also classified as a non-polar bond, because the electronegativity difference between these two is very small. Now we're going to get into the exact electronegativity difference that's required a little bit later when we compare all three bonds, but just know that this right now, the electronegativity difference is very, very small. Now you can also have atoms that share electrons unequally. So not all electrons are shared equally between them, and they tend to gravitate towards one side or the other. For example, fluorine has an extremely high electronegativity value. If I were to bond it with something like nitrogen, those electrons in the bond tend to gravitate towards fluorine. It's not that they've been removed from nitrogen, they're just not in the middle anymore. Here's the middle, and they've gravitated towards the fluorine. Well, because of that, it's going to create what's called a partial positive and a partial negative charge. Okay, that's what we see here. Oxygen has a higher electronegativity value than hydrogen, so what it's done is it's actually pulled the electrons closer to oxygen, not away from hydrogen altogether, but it's pulled them closer to oxygen. Because of that, we have a partial positive and a partial negative. Now this partial positive and this partial negative actually give it some interesting properties. Because of this, the polar covalent bonds tend to be stronger than the non-polar covalent bonds, okay, because you have this partial positive and partial negative, and you have Coulomb's law. Okay, so there's going to be an attraction between the partial positive and the partial negative charge. So this tends to be a stronger bond. The atoms are held closer together, as opposed to the nonpolar. Whenever you have a nonpolar bond, there is zero charge and zero charge. So because of that, that's not nearly as strong of a bond. Now ionic bonds are even stronger than that because they have full positive charge and full negative charge. We'll get to that more in detail when we compare these. So just a review of electronegativity. Electronegativity is a measure of an atom's ability to capture an atom. It depends on everything we talked about as far as Coulomb's law and effective nuclear charge. So it's the tendency of something to want to capture an electron in a bond or pull it closer to itself. You should know that the electronegativity trend goes up with increasing electronegativity and to the right with increasing electronegativity, and that the most electronegative element is fluorine. Okay, when we talked about this, we wanted to compare the different bonds. So remember, the polarity of a bond is determined by the electronegativity, or the change in electronegativity between the two atoms. For example, when you look at chlorine, the chlorine has the same number for both atoms. So whenever you calculate the change in electronegativity, I don't remember what chlorine is, but like say it's 2.5, 2.5 minus 2.5 is still 0. So because of that, this thing is 0 and it's classified as a nonpolar bond. Now the change in electronegativity, if it's less than 0.5, some books will say 0.4. It depends on the book. There's not going to be anything that close for you to determine. But if it's less than 0.5, it's nonpolar. Now if it's less than 1.7 and greater than 0.5, it's called a polar covalent. And anything that's greater than 1.7 is considered to be an ionic bond. Now notice that these are not absolutes. Because there's a range, we tend to define them as increasingly ionic, or increasingly polar, or increasingly nonpolar. An example of that would be if I have an element, or excuse me, I have a bond that has 0.1 as its change in electronegativity, that's going to be a certain polarity. Now if I move up to 0.4, both of these are still nonpolar, but one of them is more polar than the other. So you would say when it's 0.4, it's more polar than 0.1, even though both of them are classified as nonpolar. And I know it gets confusing because it sounds like we're mixing up our definitions there, but we'll get some practice on it. So next it says covalent bonds. It says the bonds can be represented by the Lewis structure. You see diatomic fluorine. So whenever you share these two electrons, instead of representing the two shared electrons, we actually draw them as a line, showing that it's a bonded pair of electrons. So that line represents electrons that are shared between the two atoms. So, using your periodic table with the electronegativity, determine an element that will form a nonpolar bond with nitrogen. Now, the easiest one for that is nitrogen. Okay, if you were to find nitrogen, nitrogen would have the exact same number as nitrogen, so together they would form a nonpolar covalent bond. Now what I'd like you to do is look at the table of electronegativity and see if you can find a second or a third element that would form a nonpolar bond with nitrogen. The molecule CH4 shows a tetrahedral shape as shown. Determine whether the molecule as a whole is polar or nonpolar using your periodic table with electronegativities. Now if you were to look at the difference between carbon and hydrogen, it is less than 0.5. So because of that, each one of these bonds is considered to be nonpolar. But you have to be careful. Just because each bond is nonpolar doesn't mean that the atom as a whole is nonpolar. You have to look at what's called the molecular geometry. You have to say, is there some sort of net pull in one direction or the other? So for example, just for a second, I'm going to pretend like this atom is not here. And if that atom is not there, you would definitely see a net pull of the electrons towards the carbon, and you would see a pull one way. Now, because this hydrogen is here, we have symmetry. If you were to look, there's a line of symmetry right through here that says every time I pull this way, I pull this way and they cancel out. Every time I pull this way, I pull this way and they cancel out. So there's a line of symmetry. It wouldn't matter if this element was fluorine and it was highly polar. Because of the geometry, it's pulling in the same direction, so the molecule as a whole is nonpolar. So in our original example, each bond is nonpolar, the molecule as a whole is nonpolar. So we can determine that based on the difference in electronegativities and if we can determine a line of symmetry. The electronegativity and the size of the atom will determine how long a particular bond is. So whenever you're looking at bond formation, realize that the electrons between the bond have to come to what's called an equilibrium in between the two atoms. So for example, if I have a nucleus, we're going to take it easy right here. We're just going to say that we're talking about a hydrogen atom. So the hydrogen atoms each have one electron, one valence electron in them. So whenever we form a bond, these electrons have to migrate to be in between the two atoms at an equilibrium position. For example, if I have this situation right here, that right there may not be energetically favorable because these protons are too close to each other where they would repel from each other. And if I do this, where I spread out the protons and I put the electrons in between, that may not be energetically favorable either because the attraction between these two is not sufficient to hold the bond together. So instead you have to look for the point where it reaches what we call equilibrium, or where the attraction between the electrons, the attractions between the nucleus and the electrons, the attraction here is negated by the repulsion of the other nucleus. So that's where we get the equilibrium position, or the point of lowest energy. That point of lowest energy will tell you what the bond length is. Now the bond length is going to depend on the atom itself. How big is this nucleus? What's the charge of this nucleus? Does it have 6 protons or does it have 32 protons? And also the valence electrons, not just the valence electrons, but the other electrons as well. So just realize that the bond formation or the bond length is determined by that equilibrium position between the positive and negative charges. Now you also need to review covalent naming. You are also responsible for this and should be able to name any sort of covalent compound. Remember that first you identify the first compound, or the first element in the compound, moving left to right across the periodic table. But it is kind of tricky because hydrogen fits in between nitrogen and oxygen. So you've got nitrogen and oxygen, and actually hydrogen goes in between, even though hydrogen's really in the top corner on the periodic table. So you would say dihydrogen monoxide, but you would say nitrogen dihydride because of where hydrogen is on there. Now, you need to determine if a prefix is necessary. Remember, we don't use the prefix mono on the first element. We always use the prefix on the second element. And we always replace the ending of the second element with "-ide". So an example of that, it says write the chemical formula for the following covalent compounds. It's just a name or write. We're going to name this one right here. It's got 2 hydrogens. That's the first element. So we'd say dihydrogen monoxide, which we know is water. This right here is phosphorus. Okay, I didn't write mono because it's the first one. And then I would say penta because there's 5, chloride. Okay, then you have dinitrogen pentoxide. Dinitrogen means N2. Penta means O5. Finally, you see carbon. Just write carbon. There's only one of them because there's no prefix with it. And then tetra means 4. And then chloride means Cl. So you should be able to name or write the chemical formula for any sort of covalent compound. Now let's review the distinguishing characteristics between ionic and covalent. The first thing that you need to realize is there is no clear division. You have to describe something as increasingly ionic or increasingly covalent. Polar covalent compounds and ionic compounds are actually both dissolved by polar substances. And the reason why is they both possess a positive charge, be it a full or a partial positive charge. So because of that, they have a lot of similarities between polar covalent and ionic substances. So for example, water is the most common polar solvent. It has a partial positive charge and a partial negative charge. And because of that, the negative charge of the chlorine kind of orients itself towards the positive charge, and the positive sodium orients itself around the partial negative charge. Because of that, sodium chloride will actually dissolve in H2O, even though H2O is a polar covalent and sodium chloride is an ionic. Now HCl does the same thing. The partial positive aligns itself with the oxygen. The chlorine is a partial negative, aligns itself with a hydrogen. And once again, you see an example of something being able to dissolve. So this leads to the discussion of intermolecular forces. Now, intermolecular forces is a very, very important idea with regards to AP chemistry. If you were to look at this, you have a couple of different descriptions of intermolecular forces. Now, when we talk about intermolecular forces, we're talking about between molecules. So not within the same molecule, but between molecules. So for example, you see water right here. There are multiple waters that are surrounding something. Now, intermolecular forces explain why the properties of large amounts of molecules have something like a high melting point or a high boiling point. Now, water has a covalent bond. And so because it has a covalent bond, it tends to be very, very low melting point and very, very low vaporization point. But because of the structure of water, because of the intermolecular forces associated with water, water has a higher boiling point and a higher melting point than you would predict based solely on the idea that it's a covalent bond. So first of all, intermolecular forces tend to be called van der Waals forces. Okay, van der Waals forces describe all of the intermolecular forces. So whenever we say 3 is van der Waals forces, we're just saying these are all different examples of terms that represent intermolecular forces. Now the first type of intermolecular force is called a dipole-dipole interaction. Whenever you have a dipole-dipole interaction, what you have is between different molecules, you're having an interaction between some sort of pole or some sort of polarity. So for example, if you look at sodium chloride, you have sodium plus, chlorine minus. Between molecules, so if I have another sodium and another chloride, between this molecule and this molecule, there's an attraction where the sodium is attracted to the chlorine here. Because of that, that requires extra energy to pull these things apart, and is one of the reasons why sodium chloride has such a high melting point, because of this intermolecular forces. Now, whenever you have something that's a dipole-dipole interaction that involves hydrogen, it's called a hydrogen bonding. Now, hydrogen bonding is really important with water and with life. Okay, whenever you look at DNA, the DNA is held together in the strands by hydrogen bonding between the two different nucleotides. So if you were to look at hydrogen bonding represents what we see right here. Whenever we see the positive hydrogen has a partial positive charge, and the negative here has a partial negative, and those two things are attracted to one another. So because of a dipole-dipole interaction involving hydrogen is called hydrogen bonding. Now notice these intermolecular forces don't have to be a full positive charge or a full negative charge. It can consist of partial positive and partial negative. Okay, so that's one of the things they can be for intermolecular forces. Van der Waals we've already addressed. London dispersion forces are a little bit different. I'm going to scroll down just to get a little bit of room. Now, if you had hydrogen bond with hydrogen, we already said that that's a nonpolar molecule. Okay, nonpolar molecule means that the electrons are shared equally between the two. Now, remember that when we draw these electrons right here, the electrons are not static, so those electrons are moving around. Now, occasionally, just due to random chance, these electrons will move closer to this hydrogen as opposed to this one. That's just, it's not a permanent thing. That's the difference. Whenever we have it with water, it's a permanent positive, partial positive, and a permanent partial negative. Okay, with this one, it's just a temporary movement of the electrons, which would cause a very, very slight partial positive and a very, very slight partial negative. Now, in a brief instant, this thing is going to go back to the middle, and it could go back even to the other side. So this represents the attraction between two different molecules, hydrogen and hydrogen, that because of the instantaneous position of the electrons, it makes a temporary instantaneous dipole, which causes a slight attraction. This is by far the weakest of all of them. Okay, the dipole-dipole interaction tends to be the strongest. Okay, hydrogen bonding is also strong, but the London dispersion forces is very, very, very weak. So atoms can be bonded by more than one pair of electrons, and we call that multiple bonds. Now, whenever you're looking for multiple bonds, the usual suspects are carbon, nitrogen, and oxygen. Not coincidentally, those are the ones that tend to be involved in life. The flexibility in being able to form multiple bonds has kind of led to the development of life based around these three molecules. So here's an example that you see right here. Everything's trying to satisfy the octet rule, and when I'm trying to look at the substance C2H2, which you should be able to name as ethyne, okay, when you look at this substance, the octet rule is not satisfied whenever you have this right here. So you have to say, I can't just do carbon, bond, carbon, hydrogen, because when you do that, there's an electron deficit of this carbon for 4 and of this carbon for 4. So because of that, you have to create what are called multiple bonds. So instead of these things just sharing one set of electrons, they actually share 3. Now the process for finding multiple bonds can be kind of tricky. So the first thing that you want to do is you have to pick a central atom. Now the central atom you generally want to be the one that's unique, or the one that there's one of, as opposed to when we look at carbon dioxide, okay, there's two oxygens, and so we tend to not make that the central atom. The central atom, you want it to be generally carbon or nitrogen because it has more opportunity to make bonds. Okay, so if you were to look at this, I've picked a central atom, and then you count the total number of valence electrons. Okay, this oxygen has 6 valence electrons, this one has 6, and this carbon has 4. So because of that, I have a total of 16 valence electrons. Now, what I do now is I connect the atoms. Whenever you connect the atoms by a bond, they're now connected to each other, but you've lost 4 electrons. 2 electrons here and 2 electrons here. So because of that, I have to subtract 4 total electrons from my total, leaving me with 12 possible electrons. Now the next thing I need to do is I need to count the electrons necessary for each atom to satisfy the octet rule. Now remember, this oxygen thinks that it has 2, so it needs 6 more. This oxygen thinks that it has 2, so it needs 6 more. Now this carbon actually thinks that it has 4, so it needs 4 more. So the total electrons needed is not 18, but 16. So now, if the number of necessary electrons equals, fill it in. So for example, if I need 18 electrons and I have 18 electrons, I would just fill in the electrons and I would be done. But because I have 12 electrons and I need 18, there's what we call an electron deficit. So what I would need to do is I would need to add in a double bond. Okay, I would add in a double bond and I would subtract 2 more electrons from my total. Okay, when I subtract 2 more electrons from my total, I would say, okay, well, I still have a need. And then I would do it again. I would add a double bond. And I would see that my available electrons equals my total need, and then I can fill my electrons in. And I can see that carbon dioxide consists of 2 double bonds to carbon. If you look, carbon has no free electrons attached to it like oxygen does. So it says draw the Lewis dot structure of perchlorate. You should know what perchlorate is because you've memorized your polyatomic ions. You would say perchlorate is ClO4 with a minus. This minus indicates that I have one extra electron. So when I look at chlorine, chlorine goes in the middle because it's the one that there's one of. And I would say, okay, chlorine has 7 valence electrons. I know chlorine has 7 valence electrons because it's in the halogen group next to the noble gases. Next, I know oxygen. Each oxygen has 6 valence electrons. There are 4 of them. So I would get a total of 24 electrons from oxygen. Added to the chlorine, that's 31. Don't forget the minus sign. I have 32 available electrons to make this molecule. So the first thing that I need to do is I need to surround the atom, the central atom, with the other atoms, and I need to bond them together. When I bond them together, that lets me know that I had 32 available electrons, but I just used 8, 2 for each bond. So now I have 24 available electrons. And I would look, chlorine doesn't need any more electrons because it's considered to be satisfied by the octet rule. Now, if I were to look at oxygen, each oxygen thinks that it has 2 electrons, so it needs 6 more electrons. There are four different oxygens, so I need a total of 24 electrons. Since my total electrons available and my electrons needed are equal, I can just fill in and I can say, okay, that means that the dot structure would be this. And you'd fill in your electrons. Now you would also want to indicate that this is a minus charge. So you would say that this right here is what we have for a perchlorate ion. The compound CH2 cannot be formed by stable covalent bonds. Explain why not and justify your answer using the clear method. So the first thing that you would recognize is you have carbon. Carbon has 4 valence electrons and each hydrogen has 1, making 2 total electrons from hydrogen. So I have 6 electrons that are available. So what you would do is you draw the carbon in the middle, and then you would attach it to a hydrogen, and you would attach it to a hydrogen. At this point, you've used 4 electrons, and you have 2 electrons left. Now carbon thinks that it has 4 electrons, so it needs 4. So I have a deficit because I need 4 electrons and I only have 2. Well, at this point you would start to look to double bond to something. But the problem is that hydrogen is satisfied with just the 2 electrons that are present. So I don't have the ability to double bond to hydrogen. So because of that, these 2 electrons would go here. And you'd say you'd have an electron deficit on carbon. Carbon does not satisfy octet rule. Because of that, this is considered to be not stable or not energetically favorable. Formal charge. Formal charge is designed to determine if a structure is efficient in its electron distribution. Atoms tend to arrange themselves in ways that reduce the charge on them. So you're not going to see something that's going to be negative plus negative because you can rearrange this atom so that these two can cancel each other out. Atoms tend to do that. They tend to make it so that there's no charge, no formal charge on a particular element. So when you look at a molecule, you have to look at the formal charge on each atom. The formal charge is calculated by the number of valence electrons it should have, okay, and then you subtract the number of electrons that it actually has. So you take the number of valence electrons that it should have, and you subtract the number of free electrons, and then you subtract half the bonds. Okay, for example, if you were to look at this oxygen right here, this oxygen should have 6 valence electrons. That's where it is on the periodic table, group 16. But it has 1, 2, 3, 4, 5, 6. That's where that 6 comes from. And then it has half of one bond. Half of one bond, remember a bond is 2 electrons. Since it's a bond of 2 electrons, then you would go ahead and say half of 2 is 1. So that's where that 1 comes from. So now if we look at nitrogen, nitrogen has no free electrons. It's supposed to have 5, but it has 1, 2, 3, 4 bonds attached to it. So 5, which is what it's supposed to have, minus 4, because it's got 4 bonds, half of that would be that, so you'd have a total charge of 1. So now resonance structures. Resonance structures are ways of manipulating atoms in such a way that you're looking at whether or not it's stable. You're looking at the formal charge to see if it's distributed evenly. Now the resonance structure, the key thing for a resonance structure is not changing the connectivity of the molecule, just the arrangement of the electrons. And that's the biggest thing. You can move the electrons on to make a double bond or a single bond or 8 valence electrons as opposed to 6. But you cannot move or change the connectivity. I can't take this oxygen and move it over here and say NO. It's no longer the same molecule at that point. So that is not a resonance structure. If you were to look, here's the resonance structure. Right here, I have a double bond here, and what I'm going to do is, this is a negative charge. I'm going to take those 2 electrons and I'm going to move them down here. When I move them down there, it creates a double bond. But if you were to look, now nitrogen is not going to be stable. So since nitrogen is not going to be stable, it's going to take these 2 electrons and kick them out to this oxygen, which is where I get this resonance structure right here. And then the next one, you're going to take these electrons, you're going to move them down here, and whenever you move them down here, you get this third resonance structure right here. So the key to a resonance structure is it's the same thing, you're just moving around the bonds to make them look different. So an example of this would be, remember how we had carbon dioxide? And we said, okay, if you were to look at this particular atom, carbon thinks it's supposed to have 4 as far as its formal charge. Carbon thinks it's supposed to have 4 valence electrons, and it's got half of the 4 bonds, so it's good and it has a charge of 0. Oxygen, remember we had to fill it in here. Oxygen thinks that it's going to have 6 electrons, and if you look, it's got 4 electrons and then half of the 2 bonds, so it has 6 electrons and it has a charge of 0. But I could draw a resonance structure for this particular element like so. I could take these 2 electrons and I could put it down there. And when I did that, I would get oxygen triple bonded to carbon, which would be double bonded to oxygen, and then we'd have this right here. The problem with this is this particular resonance structure is not stable for a couple of reasons. And this would not be considered to be a valid resonance structure because you've got a triple bond to carbon and you've got a double bond to this carbon and the oxygen, so this thing right here does not satisfy the octet rule. What I could do though is I could kick these electrons out here and I could have oxygen, triple bond to carbon, single bond to oxygen, 1, 2, 3, 4, 5, 6. So all I did was move the electrons around. This right here, this original structure, the carbon dioxide, is the same. It's got the same connectivity. The only thing I did was I moved the electrons around. Well, when I do that, you'll notice that the formal charge no longer matches up. The formal charge of each element here was 0. But if you were to look at the formal charge of each element in this bottom example, you would see I've got 1, 2, and then half of the 3 bonds, this has 5. The problem is that oxygen thinks it's supposed to have 6. So because of that, this oxygen has a charge of +1. This carbon right here is good. It's got half of each one of the bonds, so it's 0. But this oxygen right here would have 1, 2, 3, 4, 5, 6, plus half of this bond would be 7. But remember, it thinks it's supposed to have 6, so this would have a charge of -1. So because of that, this is a more unstable version, because there's a way of arranging these molecules that you have 0 charge. So this version of carbon dioxide is much more stable than this version of carbon dioxide. Alright, you should also be responsible for looking up the exceptions to the octet rule from page 312. You should be able to calculate the lattice energy formation on page 295 and the oxidation numbers and formal charge relationship on page 309. So reference your textbook for those and ask any questions that you have in class.